All right, howdy folks. Welcome back to Professor Carbon. And in this video, what we're going to do is discuss an arrow pushing mechanism for this iodolactonization reaction. And we call it an iodolactonization because we're going to take the alkene in the starting material. We're going to form an iodine bond on one side, so the iodo part, and then we're going to end up making a lactone on the other side. And remember that even though this is an ester functional group here, when the ester is part of a ring, we call it a lactone. Okay, the mechanism here is going to use a kind of an unusual reagent, one that we haven't seen particularly often, but there's a hint here that this behaves like I+. And so I+, of course, is a electrophilic center. And so we should use that to engage the alkene as a nucleophile. Now, with all of these videos, it's very important that you take a few minutes and pause the video, work through the problem all on your own before you just follow along with the answer. And so I'm going to encourage you to pause the video right now. Okay, coming on back into the video here, what I'd like you to do now is just talk through the reagent. And K, I3 is a little bit atypical, and so we have a positive here, and then overall this polyatomic iodine anion. And the way that this is formed is from molecular iodine, I2, along with potassium iodide, and then the iodide attacks I2 to make this complex ion. And overall, it's kind of an unusual looking one because we have three iodines bound together, and overall the whole thing has to be minus, but the center iodine here has one bond too many, and so we might give that the formal plus charge, and then we might make all the iodines on the side kind of minus. The really important thing, though, is that one of the iodines on the edge here are going to end up being attacked, and then we'll end up liberating free molecular iodine. For the sake of arrow pushing simplicity, I'm just going to call this thing I+. By the way, other iodinating reagents that we might use instead for a very similar transformation, remember, might be N-iodosuccinimide, which is shown here. So NIS is sometimes what this is called or abbreviated as. It too is polarized so that we have something that's effectively I+ on this side. All right, I'm just going to clean up this line here, and then we're going to start with our I+. So I'm just going to write that on out. And most alkenes then are good nucleophiles. And maybe not good nucleophiles, they're at least weak nucleophiles. And so they'll engage very powerful electrophiles. And that is exactly what it's going to do with I+ here. Now, whenever making a halonium ion intermediate, I almost always forget about the second arrow that we need to come back in. And the reason for that is that the product is going to have not one, but two bonds to iodine. And so we're going to make sure that we account for both of those. One bond going from the alkene to iodine, and then the other arrow coming back to form the second carbon iodine bond. Okay, now it's conceivable because we have a complicated starting material here with multiple stereocenters. And let me just highlight those stereocenters. There's actually three different ones already in the starting material. And conceivably, this iodonium ion could form from either the top side or the bottom side. So in principle, we could end up with a mixture of these compounds. And so let me just draw out the other one here in black. And it gets a little complicated to worry about which one we're going to form first. And often we worry about issues in of diastereoselectivity, and we use that term because these two molecules are diastereomers of each other. They're stereoisomers that differ in at least one stereocenter, but they're not superimposable mirror images. So they're not enantiomers, they're diastereomers. And often we leave complex issues of stereochemistry until one gets to a graduate level course to go ahead and discuss how you form that. In this particular case, it's actually complicated because sometimes these formations of iodonium ions can be occasionally reversible. And so it might be an issue where it's going on and coming off, and then one of the other products is the one that ends up ultimately reacting. Okay, and so from here then, I'm just going to take a moment to actually draw out the carboxylic acid all the way on this structure that I have. And we're going to put the carbonyl there and then OH over on this side. And this is going to be our nucleophile. And what I really kind of find fascinating about this reaction is this iodonium ion in principle could be attacked either by this oxygen or by this oxygen. And so we have two different potential attacks. And what ultimately wins out is going to be the acid functional group, which is kind of cool. I'm just going to delete that so that we don't get confused. I'll just delete this as well. Okay, and so if that attacks there, then we're going to need to engage our leaving group and break that carbon iodine bond. So I'm going to add a second arrow. And now I'm going to have the oxygen, and that's going to mimic the stereochemistry here. And the reason for it is 5-membered rings are almost always going to be cis if they're fused to another 5-membered ring. And the reason for that is the trans 5-5 ring fusion is going to be quite strained. And because that group is already kind of dangling down on the bottom, it's going to be able to attack from that preferred bottom face, just like it's bridging. Okay, now we've got positive charge there, and then our OH group on that side, and now we have our up iodine, like so, OH over here, and then our wedge, OCH3. And so this is kind of a cool one, and now what we're going to do is we started out with in water. And so we're going to engage that water now is going to be probably the most basic group that's floating around to ultimately deprotonate this system. So I'm just going to add my water right there, have that pluck off, and then I'm going to move those electrons right over. And so that'll generate the product then, and some H3O plus. And that H3O plus then is going to be balanced out. Remember when we started with I plus, then we should end with something that's plus as well. Okay, so that's the mechanism here for this iodolactonization reaction. I believe this is an intermediate in Corey's synthesis of the prostaglandins, which is fun. So if you're interested in how we put together more complicated more complicated molecules, I'd encourage you to visit total synthesis web pages such as Syn Archive or organicchemistryportal.com. Also, you could visit the webpage organicchemproblems.com, and that also has a list of more complicated organic chemistry problems. Lastly, for those of you that have been watching and utilizing these videos, I hope that you'll become a subscriber to the YouTube channel. Also, feel free to like us on social media or leave us comments in the feedback sections below. Lastly, if you'd like access to the PDF notes, either before or after they're filled out, you can go ahead and become a subscriber to our Patreon page, and then you'll be able to download those within the supported links. All right, so that's it for this video. Please enjoy the next video.